Deutsch from the University of Washington School of Oceanography. Dr. Deutsch's research is aimed at understanding how climate influences the basic functioning of ocean ecosystems. He combines data analysis and numerical models of the ocean to determine the sensitivities of biogeochemical cycles to climate and human geological timescales. He is interested in how small bacterial depleted oxygen levels will lead to large regions of low oxygen in the world's oceans. Dr. Deutsch is the Cobley Frontiers Fellow, and I asked him what the Cobley was, and he doesn't know. I suspect it's those Norwegian biscuits, like a biscuit company or something. But anyhow, he holds that fellow at the School of Oceanography in Washington. He got his BA at Oberlin College, his PhD at Princeton, postdoc at University of Washington, a brief stint at UCLA, and then returned as an associate professor to the University of Washington in Seattle. Curtis will speak on aerobic marine habitat in a warming climate for microbes and macrofauna. Welcome.
Thanks very much. Thank you. First, let me start by expressing my real appreciation for the invitation. It's incredibly, very honored to be among the eminent scientists speaking here, and I'll try to live up to their very high standard. And for that reason, I will not start with a joke. Ellen set way too high a bar. Instead, I'm just going to jump right in the deep end with a slide that will set the stage for everything that I want to say today. And it's really a slide that I think encapsulates Ocean 101 for anyone who's interested in oxygen, but I think it shouldn't go unsaid. This is actual observations, climatological observations of oxygen concentration right through the center of the Pacific Ocean. So Antarctica is on your left, and some kind of Aleutian Island is on your right, or almost Aleutian Island on your right here. And we've got the surface ocean broken up into one depth band, the thermocline in this middle band, and then the very deep ocean, nonlinear depth scale. And just to set a couple of quantities in your mind that I'll use periodically through this talk, the surface ocean is a particularly simple place with respect to oxygen, or perhaps oxygen is a particularly simple quantity in the surface ocean because it basically follows a well-known thermodynamic solubility for any gas in the ocean. That is that the gas exchange is fast enough to maintain the surface ocean very close to equilibrium with the atmosphere. And that means that we can predict the oxygen concentration within the surface turbulent mixed layer reasonably well if we just know its temperature, and if we want to be really precise, its salinity as well. So you can see that as you get toward the tropical surface ocean, you find very relatively low oxygens, about half of the maximum oceanic oxygen. As you move toward the poles of either pole, you get toward cold water, and the highest oxygen that you find anywhere in the ocean, something like 350 micromoles per liter. Now, in the deep ocean, we have a very different balance. It's not between gas coming in and gas going out, but rather it's a balance between oxygen that's constantly being consumed as particle matter and dissolved organic matter falls or is transported into the deep ocean, and that draws oxygen down, so that we start to see these blue colors reflecting relatively low oxygen here. So there's a balance between that respiratory oxygen consumption on the one hand and the physical transport of oxygen that's always replenished from the surface ocean along the pathways of the large-scale oceanic circulation. So that's illustrated by this white arrow here, and the white arrow is sort of following a typical kind of ventilation pathway for the thermocline of the ocean, which starts at the surface in kind of mid-latitudes, and then it works its way toward the tropics under the influence of the wind-driven circulation, eventually upwelling either along some kind of coastal boundary in the eastern ocean basins, or more likely at the equator, the well-known equatorial upwelling. So within the ocean interior, and I'm going to ignore the deep ocean for most of this talk, within the ocean interior we can also predict oxygen reasonably well, but we need to know a couple of things. We first need to know we need to know the oxygen that the water parcel started with, but we know that because we can just measure its temperature. And that tells us how much oxygen saturation the parcel would have started with. But the oxygen, of course, is less than that because over some time it took the water to get there from the surface ocean, indicated by this symbol tau. There's been this average rate of respiration, R with an over bar, sort of the average over the lifetime of this particle through its transit. So we could predict oxygen if we knew the rate of respiration and the time it's been undergoing respiration as it transits through the deep ocean. So we're going to make use of some of these quantities, as we'll see later on. But first, the question is, why would we care to understand the oxygen cycle? And there's a whole host of reasons, but the two that I think will be most appealing for this audience are also the two that have largely driven my research over the past few years, and that's what I want to talk about today. The first of those is that as you begin to deplete oxygen from, again, its sort of maximum values that you find in the surface ocean down toward truly anoxic levels, no detectable oxygen, even with very precise sensors, the fraction of all species whose oxygen tolerance has been measured that can survive under those conditions begins to decline. Now it declines in a very nonlinear way. At first, you can get about halfway to the complete depletion of oxygen, and still, no matter what your favorite taxonomic group is, most species can still survive under those conditions. But you reach something like between 100 and 150 micromoles of oxygen per liter, and suddenly a little decrease in oxygen leads to a large reduction in the number of overall species that can survive under those conditions. This is just a compilation of data throughout the literature. And when we look at the distribution of those kinds of low oxygen conditions, again, we want to look at those parts of the thermocline ocean, the mid-depths, and in a spatial view here, you see that those are largely concentrated in the Pacific Ocean and in the tropics of all three oceans. So we've got the Indian Ocean here, the tropical Pacific, and to a certain degree the tropical Atlantic. Also some regions along coastal boundaries and also in the large subarctic Pacific Ocean. So all those, you can't see the numbers down here, anything from sort of green on down in this view at 300 meters is already within the region of the range of oxygen concentration, starting to preclude certain species from living in the ocean. So that's one reason we are interested in oxygen from the point of view of large animal life, macrofauna. But there's another reason. As we get toward zero oxygen and habitability for virtually all large animals goes to zero, of course we find the predominance of anaerobic microbial life. And I don't have any nice pictures of them. They're not terribly charismatic anyway, but we can see what they do. Sorry for those who study them. We can see what they do over time in the ocean by looking at the nitrogen that they have removed from seawater. And it's easiest to see that if we reference the nitrogen and the nitrate concentration, the largest reservoir of fixed nitrogen in the ocean. If we reference that concentration to something like phosphate, which is not removed by microbial processes under low oxygen conditions relative to. Okay, so what we see then is this is a measure of that nitrate depletion. So 0 is no depletion, and minus 20 is a very strong depletion. That's about half of the maximum of the highest kinds of nitrate measurements that you find in the ocean. And we see that those extreme nitrate depletions are found all in the regions of the eastern tropical North and South Pacific and in the Arabian Sea, also in certain broad productive shelf regions, which I will not talk about in this today. But these areas, you can see in the oxygen map that I showed you before, also correspond, if you look really closely from the front of the room, are the very deepest dark blue. Those are our three, and what's often called functionally anoxic. The oxygen is, there may be a tiny, tiny bit of oxygen, but it's undetectable even with modern technology. So we can see the microbes just depleting the ocean's reservoir of nutrients in these tiny little pockets of the ocean. They account for 0.1% of the ocean's volume, but they perform about half of all the nitrogen removal from the ocean. So these tiny little pockets exclude the macrofauna, but they're critical habitats for these anaerobes, and they do a pretty bang-up job of removing the nitrogen that ultimately is needed to sustain the plant life in the surface of the ocean. Okay. So all that leads to a question about how the oxygen distribution should change as we warm up the climate. And this is a slide that will just illustrate something you've probably heard many times, but I think says in pictures what intuition doesn't always fully convey. And the first part is that, as I said before, all gases' solubility declines in warmer water. So as you warm up the ocean, of course, gas solubility goes down, and that will deplete oxygen. That's the easy piece. The harder piece is that, again, that rate of transport of oxygen-rich surface water into the ocean interior can be slowed by an increasing density stratification of the ocean as it warms from the top down. And so as the oceanic circulation slows down, you expect a reduced supply of oxygen just from the physical flow. And one way to visualize that is to look at the age of water in the ocean as we would simulate it in a relatively high fidelity three-dimensional circulation here from the echo circulation. If we just tag water with a 0 age at the surface and then let it circulate into the interior and keep track of how long it's aged with respect to the flow and the mixing of waters around it, we find that you get this pattern where waters in the tropics are relatively old. There's old, very abyssal water upwelling in the Southern Ocean. There's old water in the upwelling gyre of the subarctic North Pacific. The rest of the ocean is varying degrees of youngness. Now that pattern should look familiar because it's essentially the inverse of the pattern of oxygen that we saw before. So if you want a first order explanation for why oxygen is low in the places that it's low, it's because the water is old. Now that leads to an interesting prediction, of course, that is, if you were to slow down the oceanic circulation and these ages were to rise, you expect oxygen to fall. Okay? Now, the simplest expectation is that circulation, if it slows everywhere, will raise the age everywhere. And we'll come back to that in a moment. But for now, this would lead you to think that the loss of oxygen has been called deoxygenation. It's a very simple thing. Oxygen should just go down everywhere. But that's not what we actually find in model simulations of a warming climate. Although it's a reasonably good first approximation. This is an average over many different model simulations of the future, of our current century, the next 85 years under a continued rising of CO2 in a global zonal mean, so averaging around latitude circles at all depths down to the bottom of the ocean. Oxygen in the blue and turquoise is declining over this century relative to a pre-industrial value. And you see basically blue and turquoise almost everywhere except for right here in the tropical thermocline where things are approximately white, which is to say that oxygen is very stable even after 100 years. Okay? Another way of looking at that is just to plot the mean of the upper 1,000 meters. And there we pick up some similar features where the mid and high latitudes are very clearly losing oxygen in some places, like the North Pacific, quite dramatically, up to 50 micromolar oxygen reduction. So these are substantial fractions of the existing oxygen predicted to be depleted. But if you look at the tropics, again, the colors get very light. And in fact, in some places, oxygen could even rise according to these model simulations. But of course, these are models, and we don't believe them without further interrogation. But at this stage, what we would say is that in mid and high latitudes, going back to our kind of simple expression for oxygen, it's very clear that oxygen saturation goes down because it gets warmer. The oxygen goes down not only because of that, but because the age of water gets older. Let's not worry about what happens to respiration quite yet. In the tropics, we get an oxygen change that it has an unclear sign. In some places it goes up, some places it goes down. They're both very small changes, which suggests that the declining solubility of oxygen is compensated by some kind of reduced time-integrated consumption of that oxygen along the flow paths of the mean circulation. And I'm going to come back to that in a minute. So here are the two questions that I would like to pose based on everything I just said. They both are motivated by the question of how does climate influence ecosystems through these three combined set of properties that I've just described. The first one being temperature, second oxygen, and third nutrients. And I'm going to divide the talk into two parts. The first part is to combine temperature and oxygen to understand how the warming climate perturbs the aerobic habitat of marine species. The second part of the talk is going to ask how does climate warming impact those anaerobic habitats that are dominated by the microbes that, again, keep the ocean nitrogen limited. Okay. So since this is a session on extreme events, I thought I should at least remind you of something that you already know, which is that oxygen, for macrofauna, oxygen is clearly capable of doing great disruption to marine ecosystems, and this has been dramatically illustrated in your own backyard, many, many times on an almost annual basis. But it was also apparent along the relatively less disturbed or less human-influenced west coast of the United States in the Northern California Current off the coast of Oregon, where in a very short period of time, we go from a benthic community that's relatively healthy here to one that was essentially a dead zone. And this was observed for a couple of years in the first decade of the 21st century. It's since gone away, but there are clearly episodic events in an ocean, more or less removed from the dramatic kind of nutrient inputs that you have in the Gulf of Mexico. And it just shows that, in an extreme event, oxygen clearly can wreak havoc. Now, I think I can mostly skip over this slide because it was so nicely covered on slightly shorter timescales by Ellen yesterday, but it just also reminds us that over geologic timescales, an extreme event, if you want to call it an event, associated with rapid warming of the climate can also cause massive extinctions. And now this we can't necessarily clearly attribute to oxygen, but it is one of the main hypotheses why at the end of the Permian, going into the Triassic period, so the Permian here with relatively high species richness and relatively cool waters as you move upward in time. Into the Triassic, you get this rapid warming, a very large loss of genera and land and on land and in the ocean. One of the main hypotheses for this, although it's far from settled, is that a massive or widespread anoxic deep ocean could have caused this kind of thing. So I'm really just trying to fit into the theme of the session with extreme events, but what I really want to know is, do we only care about extreme events? Is there something about the distribution of oxygen that actually influences the distribution of species, even in the average state? Okay? Leaving out the extreme events, which obviously have an influence. So the first part, the method I want to, remember the question is, does hypoxia constrain the average contemporary distribution of habitat for marine species? And to do that, I want to pull together some different strands of data that I think will give an affirmative answer, and I'll try to convince you that that's the case. The strands of data include laboratory data, demographic data, and climate data. And what I want to ultimately do is estimate the so-called metabolic scope for a variety of marine species, and I'll come to what that means in just a moment for those who aren't familiar with that terminology. The first inspiration for this, for me, came from this paper by Hans Portner, who showed that the effect of temperature, on the x-axis here, on the daily growth rate of a fish from the North Sea, I believe, an eel pout, was sort of characteristic of most kinds of species growth rates, bell-shaped but skewed to the right. The interesting thing, though, is that he posited that this could be explained, at least on the right-hand side, where the warming causes a decline in growth, by a convergence of oxygen supply relative to demand. So the black curve here is the oxygen in seawater. That's just oxygen solubility. Okay, so it's not necessarily what every species would be exposed to, but in the surface of the ocean, it would be a good prediction. And on this dashed curve here, actually the points indicate the oxygen at which the anaerobic metabolites were building up. So the species the organisms were switching to an anaerobic metabolism. Now, with a little bit of artistic license, you can put a curve through those points, and they converge with the supply curve here at about the temperature where growth ceases. In any case, it suggests that there's some correspondence between temperature and oxygen tolerance. So the question is this a general thing, and does it really matter for species growth in the places where they actually live in the ocean? So to do that, I want to walk through creating a very simple index to try to answer this question. And it starts, again, with oxygen supply. So we're going to assume that any water breather can have an oxygen supply whose rate depends critically on the oxygen partial pressure in seawater. The more partial pressure you have, the faster oxygens can be supplied across the water animal membrane surface. But not only that, it also will depend in some way on the body size. So probably a larger body will, in an absolute sense, be able to have oxygen supplied faster. And then on some kind of exchange rate, which depends on various details of, for example, blood oxygen binding. Okay, so the key thing is that supply should depend on body size and on ambient partial pressure of oxygen. And thanks to Brad for pointing out to me that it should be partial pressure and not concentration. Okay, so oxygen demand is the other side of the organismal energy balance, or one kind of energy balance. And there we're going to make use of relatively well-used and well-known relationships between metabolic energy demand and temperature. So this is actually inverse temperature. So warmer temperatures are on the left and cold is on the right. And what you see is that log transformed metabolic rate normalized by body mass show, in the absence of any data, these are actually linear fits here,